Okay, today we'll be starting section 2.5. This will take 2 days, so this is day 1. Here's the learning targets we'll be focusing on today. Something called the fundamental theorem of algebra. We'll be covering that right away to determine the number of zeros of a polynomial function. And then we'll be finding rational zeros. I'm going to show you a way to find possible rational zeros of polynomial functions. And then we'll use that to go ahead and find all the zeros by division and factoring and things like that. Okay, so those are the 3 things we'll be focusing on today. All right, you don't have to write this part down. Let me just kind of quickly explain this fundamental theorem of algebra. If we were to analyze, these 2 functions, let's figure out the zeros for both of these. Let's do it by hand, and let's take a look at the graphing calculator. If I were to solve these and find the zeros, all right, replace y with 0 for both of them. Here I subtract 4, square root both sides, and now I get the square root of -4, which is 2y. So I'd say x equals plus or minus 2y. Here, though, we end up with a real number and not an imaginary number, and we get x equals plus or minus 2. Okay, so this one has 2 real zeros, and this one has 2 non-real zeros. It's also confirmed if we to look at the graph real quick, right? I have x-intercepts at 2 and -2 for this one. And this one doesn't have any x-intercepts, but it doesn't mean it doesn't have any zeros. Okay, they're just non-real zeros or imaginary zeros. Okay, complex numbers. Now, this leads to the fundamental theorem of algebra. This is actually still a complex number by definition. Okay, remember this is 0 plus 2i and 0 minus 2i, right? That's how we can write that in the form a plus bi. Well, this can be written as 2 plus 0i. We don't really think about that. We have the answer of just 2, but we could actually write that as a complex number, right? So it doesn't really matter, I guess, 2 and then the -2 plus 0i. All right, so that fits the definition. So that's why they word this fundamental theorem of algebra this way. Okay, if we have a polynomial of degree n, degree whatever, 3, 4, these are 2, of degree 2, then the function has at least 1 0 in the complex number system, and these both did. Okay, they had 2 in the complex number system because 2 still fits in that definition, complex numbers, okay? All right, but that is a little incomplete. I don't think that's the big picture. This is the part I do want you to write down. In summary, the number of zeros of any function, okay, will equal the degree if we include all real zeros and the non-real zeros. Okay. So in the end, it actually is a pretty fundamental theorem in the end. Whatever the degree is, it could be degree 10. Then we know if we include real and non-real zeros, a degree 10 function will have 10 zeros. Simply put, easy. Okay, pause if you need to keep writing that down. I'm going to move on to these examples. They don't take long. Okay, so determine the number of zeros of the polynomial function. Second degree, we saw up there, even though if they were no x-intercepts, we still had 2 zeros. Okay, so the number of zeros that this function will have is going to be 2. Okay, third degree, I could have 2 that are imaginary and 1 that's real. Who knows? But it doesn't matter. You're just going to throw them together. That's 3. This is 4. Okay. All right, easy enough. So that's the fundamental theorem of algebra. Let's go ahead and take a look at the rational zero tests. Okay, so we know zeros of a polynomial can be rational or irrational. Remember, irrational just means like a square root. So if I say, all right, x squared minus 4 equals 0 and solve it, we know we get x equals plus or minus 2. But if I say x squared minus 5 equals 0, add the 5, take the square root. Now it's plus or minus square root of 5. This is a rational number. This is called an irrational number. Okay, definition that it's been covered a long time ago maybe, but that's why we're reviewing it right now. Okay, so what the rational zero test does for us is it gives us these possibilities of the rational numbers, not the irrational ones though, okay? All right, so here's kind of the formula, what we do. The rational zero, I put the word possible. I think that's a good thing to include there. The possible rational zeros are found by taking P and dividing by Q. All right, what's P and what's Q? Here it is. P is a factor of our the constant term, the last term. Q is a factor of the leading coefficient. It says a sub n, so they're talking about right here. So if you have a big polynomial, it could be 10th degree, and you got all these terms in there, you can ignore everything in between. All you need to use are these numbers here. Okay, let me demonstrate for you. Change sheets. All right, so the directions say use the rational zero test to list the possible rational zeros. So I'm going to put right here, possible rational zeros are equal to, how do I get this? P over Q. So I got to take the factors of the constant term, which is the last term, a sub o, right here, right? So that's -6. So what goes into -6? Well, +1 goes into -6, and so does -1. So you do have to put plus or minus 1. Okay, let's keep making the list. Plus or minus 2 goes in there, plus or minus 3, and plus or minus 6. All go into 6. Okay, now on the bottom of this, we put the factors of the leading coefficient. So that's just 1. Okay, so what are the factors of 1? Plus or minus 1. All right. Now, since the bottom is just 1, this works out to be pretty easy. What I have to do is take 1, divide it by 1, and simplify that. So that just gives me 1. Here I got to take 2 and divide it by 1. Just ignore the signs. You're just going to put plus or minus in front of it every time. Here I have 3 over 1, and here I have 6 over 1. So we just divide them. So those are the possible rational zeros right here. Okay. All right, let me show you how it's a little bit different for 5 if a isn't just 1. So here we have possible rational zeros are equal to, remember, P over Q. What's P? P is the last term. So this is P, and then this is Q. Okay, so P over Q. That helps. All right, so what's factors of 8? 1, 2, 4, and 8. Divided by Q. Factors of 3 are 1 and 3. Okay. All right, so here's how we simplify it if we have multiple denominators. Just do one at a time. Go through and do, okay, 1 over 1. What does that give me? 2 over 1. This one goes pretty quick and easy, right? 4 over 1, 8 over 1. Okay, now move on to the next denominator. So now I have 1 over 3. She's pencil for this maybe. So I got 1 over 3, and then 2 over 3, 4 over 3, then 8 over 3, right? So I've got 1/3. Reduce them if you can, the fractions, 2/3, but I can't reduce any of these. 4/3 and 8/3. All right. Now, if you check it in the back, they'll probably rearrange it and put it in order. It doesn't really matter. It's just a list of possibilities anyways. I'm not too concerned about that. Just make sure they're all accounted for, okay? All right, I'm going to pause and turn the page. Okay, 6, 7, and 8. These are big problems. A lot of work. It's a big process. And we're going to end on this page today. What I want you to do is cross out part B. Okay, we're not going to use a graphing utility. I know everybody doesn't have access to this, so I'll show you how we can do this by hand. So write this in here, please, for part B. I'll pause and give you a moment to do that. Okay, for part A, use the rational zero test that we just practiced on the previous page. Remember, this is P and this is Q, and we're supposed to do P over Q. So P over Q will be factors of 6 go on top. Over Q, which is plus or minus 1 and 2. Okay, so go through and simplifying. We got to divide all these up top by 1. That's easy. And I'm writing fast, so you pause if you need time to catch up. Now I'm going to take all these top numbers and divide them by 2. Okay, notice what happens here. This hasn't happened yet. So I had 1/2. The next one's going to be 2 over 2. Well, that's 1. I already wrote that down. You don't need to write down a possibility twice. It's just a possibility anyways. So I'm moving on to 3/2. That's not listed already. And then it happens again with 6 over 2, right? That's 3 already listed, okay? So there's the answer to part A. Here's my possible rational zeros. Pause to catch up. Okay, now in the last section, here's the difference. Basically, in the end, if we peek to part C, determine all the real zeros, we did this in the last section, 2.3, where I said divide the function, rewrite the function, and find remaining zeros. The only difference is they gave us the 0. They gave us a 0, and then we use that to our advantage to break it down and rewrite it and do that. But now the trick is they didn't give us the 0. We only have possibilities. So out of these possibilities, we got to choose one and check to see if it's a factor or not. So I'm going to put here for start B. Start, I'm going to say start with any 0 you want. Okay, now here's the catch. Now you might be thinking, what? I got to go through and test all of these? No, it's not that daunting of a task because you're going to usually find one pretty soon. And I'll give you some hints on your OTI and your assessments of where to start so you're not, spinning your wheels all day. I get it. I'm not going to put you through that, all right? So, for example, I'm going to randomly start with, I'm going to just choose an easy number to start with. Let's go with 1, okay? So positive 1 is my 0. And I'm going to divide this function by x minus 1. Okay, so let's add, multiply, add, and multiply, add, and multiply. Okay, now I didn't get a remainder of 0. Remember, if just go back to factors 101, right? If 10 divided by 3 is 3, remainder 1, then what do we say? 3 is not a factor of 10. But 5 is, because it goes in there twice with a remainder of 0. Okay, so I need a remainder of 0 to call something a factor. Okay, the factor theorem. So to make sure we're very clear here, what do we find out here with this remainder? Because there's a remainder of -6, it means x minus 1 is not a factor. Or you could say that 1 is not a 0. That's fine. Or 1 is not a 0. Okay, maybe pause to write that down. I'm going to keep going. Okay, do you have to write this down every time? No, this is a teaching tool. You need to realize, though, when the remainder is not 0, you didn't find a factor. You didn't find a 0 that works. Okay, so I'm going to move on to one that does work. You might be wondering, how do you know? Because I already know the answers to this problem. But like I said, I'll give you hints later, okay? So when I try 3, same coefficients. Let's take a look at what happens and then how we proceed, okay? Add going down, multiply, 6, positive 3, 9, -2, -6, 0. Aha, okay, so we got a remainder of 0. So what does that mean? X minus 3 is a factor. So x minus 3 is a factor, which means 3 is a 0. Okay, both of those conclusions are drawn now. Okay, so now that we found a 0 that works, 3 is a 0. I know I have 2 more. The fundamental theorem of algebra says this is third degree. I have 3 total zeros. I have 1. I need to find the other 2. So we go on to part C. Now this is the review part. We did this in the last section. We're going to use the result of this division and rewrite the function. So 0 equals x minus 3 times 2x squared plus 3x minus 2. How did I get that? Remember, this is remainder, constant term, linear, quadratic. Work backwards. All right, and now we just got to factor this. I'm looking for factors of -4 that have a sum of 3. So factors of -4 have a sum of positive 3.